Let's talk about some narrow definition of work here. So the transfer of energy that's caused by, let's finish this sentence. A force being applied to an object as it is displaced. And even as I'm writing this, I'm like, wait a minute, force, I've done things with force before. Displacement, I know about displacement. Oh my gosh, this is like, I know about some of this stuff. Anyway, before we unpack this with a formula, I want to say, the more work you do, it must have been because you did more force. That seems to make sense. And if I've done more work, I can even say that I moved something more distance. That little alpha symbol means proportional to. Work is proportional to how much force you apply. Work is proportional to the displacement that you cause something to move by as you do that work. And so if we tie these two guys together, there's this thing that, it's actually a math thing. And there's this formula, work equals force times displacement times cosine theta. Now, if you are really into math, that's a dot product. If you're not into math, it's still a dot product. But it's force times displacement times cosine theta is going to be our narrow definition of work, okay? That's how you calculate work. And just to make sure that we have the geometry on this one, what the heck is this theta thing that you just talked about? We've seen objects sitting on surfaces before, and we've had to apply a force, let's just say, at an angle. Theta. And we've also caused that something to slide, a displacement. So we've had an applied force. We've had a displacement. Let's just make up some numbers. Maybe the theta value is 30.0 degrees. Let's just say that we push with a force of 100 newtons. Let's just say that this thing slides 10.0 meters. Say this again, proportional to. Right, so that Greek letter alpha means proportional to. If I wanted to figure out how much work we did here, we'd say, okay, well that means that work is equal to force times displacement times cosine theta. I've written my formula here. I'll sub it in. F applied was 100 newtons. Displacement was 10 meters. Cosine of 30 degrees, and people say, well, what do you mean 30 degrees? 30 degrees is the angle between the applied force and the displacement. And if you want proof of that, I can do a little bit of backtracking. Look, if I extend this arrow backwards, and I extend this arrow backwards to the point where they meet, can you guys see that we just created like an F pattern there? See how that's the F pattern for angles? That theta there, 30 degrees, is going to be the same as that theta there. In other words, these two vectors are at 30 degrees relative to each other. So that theta value is the angle between the two vectors. It's the relative angle between the two vectors. And if I hash this all out, I get 866. Is that what you guys get? All right. Head nods around the room. So 866.0254. But then we get to the units. And I'm just going to tell you, work is a way to deliver energy to something. So these are joules. These are joules of energy. Joules is the units for work.
What's in there?
Now I could round this off to 3 sig figs, 866 joules, but I want to make sure that we're all really clear about what's happening with these units. I'll do it in a quick little analysis here, okay? I see your hand. Let's be 1 sec, okay? So what we've just done is we've multiplied units of newtons times units of meters, and that's equivalent to saying kilogram meters per second squared times meters, which is equivalent to saying kilogram meters squared per seconds squared, and that is the definition of a joule.
Oh my god.
Okay? So a joule is somebody's last name, and we've definitely short formed it up, okay? Because it's a pain to have to write kilogram meter squared per second squared. So we gave it We buried it in someone's last name again, okay? But that also tells us that because it's somebody's last name, we always have to capitalize the J. Just like Newton's is somebody's last name, Watts is somebody's last name, all these capitalizations because it's people's last names, okay?
Joules has it, like Joule has a
Now,
Newton in it.
one thing that I want to throw here is, notice that I didn't say that there's a direction. Each of these two values had a direction relative to each other, but energy itself, energy is a scalar. No direction.
Huzzah, finally.
Yes. So if you're somebody that was looking for a scenario where we wouldn't have to do so many reference frames, the moment has arrived, okay? So energy doesn't require a reference frame because it's a scalar, okay? And we might have, sometimes you can already tell if there's forces involved in displacements, we might have situations that overlap with dynamics and kinematics, but whenever it's a purely energy problem, no reference frame required, okay?